Welcome to Spring LIB.
So the goal with these problems is to calculate delta G if the reaction depicted is spontaneous. And so in order to get at if something is spontaneous or not, we need to look for the standard cell potential. And so spontaneity would be positive. So that's the key to getting started here, because we don't actually calculate delta G or K according to the problem if it's not spontaneous. So we have to look in table 18.1 for the half reactions that would give us the equation that's given in the problem. So we need to find the half reactions that have copper plus and copper 2 plus. And so here they are in the table written in red. And so this is a table of reduction reactions. So we need to rearrange the equations because something's going to be reduced and something's going to be oxidized. Well, if we flip equation 1, that would put Cu2 plus on the right, which is exactly what we need. So when we flip those equations, we get everything on the correct side, so that's good. Now, we need to balance everything because that will give us the moles of electrons. And so in order to do that, we need to multiply the second equation by 2. Now, multiplying by 2 doesn't do anything to the cell potential. It just allows you to figure out the moles of electrons. But really, we should take a moment just to make sure that this is spontaneous. So because we flipped equation 1, this cell potential becomes negative. And so this, if we look in this purple part down here, this would now be 0.52 minus 0.34, which is a positive number. So this is, in fact, spontaneous. So now that we've balanced the equation, we see that the moles of electrons is 2. We know this is spontaneous, so we're going to move over to calculating delta G. So that would be delta G equals negative NF E0. When I plug in the values, 2 moles of electrons, Faraday's constant, and then the E0, which is 0.18 joules per coulomb. Remember that a volt is a joule per coulomb. So the units cancel out very nicely, moles, coulombs, and we're left with joules. Delta G often expressed in kilojoules. So when you do this math, you get negative 34.7 kilojoules. Now to calculate K, we can use delta G equals negative RT ln K. We plug in the numbers and we end up with ln K being equal to 14. Take E, raise it to both sides, cancel out that natural log, and we're left with 1.21 times 10 to the 6. Now for part B, we need to do the same thing with table 18.1, finding the equations that when combined give us the equation in the problem. So we have Fe2 plus and Fe3 plus. So we're going to look for those reactions in the table. So here are the reactions with their E0 values. Now we have to flip equation 1 because we need Fe3 plus on the right. When we do that, we actually don't even need to multiply by the 2 or 3 that I have written here, because when we do that, that flips the sign of the cell potential as this becomes positive 0.0036. Now, when you add those numbers together, you get a negative number, which is not spontaneous. So according to the problem, we don't have to calculate delta G. Now, part C, we're given the half reactions, but there's a lot of rearranging to do if it's spontaneous. And spoiler alert, it is. So if we look at the equations that are given, we do need to flip the first equation to check for spontaneity because ClO3 minus is on the right. So when we flip that equation, we're left with negative 1.21. And so when you add these numbers together, you do get a positive value. So we need to move forward. Now we need to get at the moles of electrons because we're going to be using delta G equals negative NFE0. So in order to do that, we've got a couple of complications because we have things here, water molecules and hydrogen ions that are not in the final equation. And in order to balance these reactions, we need to get rid of the water and we need to get rid of the hydrogen ion before we can balance our electrons. So the first thing, it doesn't matter which one you pick first, but it can be easier to start with the H+. So I have 3 here and 2 there. So I multiply the top equation by 3, the top equation by 2, bottom equation by 3. Then if we move down here into the purple, that cancels out our H+. So now we have to cancel out the water molecules. So now I have 2 waters here, 3 waters there. Multiply the equations by the reverse of what we did before. That gives us 6 water molecules on each side. So they cancel out. And now the electrons are equal. So we know that N in the equation that we're going to be using very shortly is equal to 12. And then we can move downward and plug into that equation. Delta G negative NF E0, 12 electrons, Faraday's constant, 0.44 is the sum of the E0s, sum of the E0s from here. So now, and again, volts is joules per coulomb. So when we multiply these things together, we get negative 509.4 kilojoules. And now we use our delta G equation. Now this number may seem very large for an equilibrium constant, but sometimes for these electrochemical equations, they can be very highly spontaneous. And this is being driven by the fact that 12 moles of electrons are being transferred on a per mole basis. So that's just a very large number for electrons, and that's why this is a very highly spontaneous reaction.